Okay, welcome. Welcome back to Launchpad. I'm Christian Reddy, your friendly neighborhood astronomer. And today we are live, coming to you from my living room. Welcome aboard. It's great to have you here on this live stream. Just trying something out. It's coming up on lunchtime here on the East Coast of the United States, and I thought, on the off chance that any of my students would like to ask me a question ahead of tomorrow's final exam, they could feel free to come in and do that here. They won't, but that's okay because we're here and there's so many exciting things to talk about going on in the solar system. First thing I have to do, of course, is just stop buffering. Let me see what I can do here to correct that. And this is only my third time ever live streaming. I really don't know what I'm doing. So if you are unable to hear me, or if I see that I'm buffering, I do apologize for that. Let me see what I can do to sort that out. Just want to welcome, while I'm doing that, let me welcome a few folks. Stony Creek Heritage Farm, good to see you, my friend. Beth, how are you? Science Games, Justin, and well, what do you know? I got a student here. Hey, Ava Ertel. Ava, you don't even need to take the. No, I'm just kidding. I'm just giving her a hard time. Thank you so much for coming by today, Ava. It's wonderful to see you. I got Boiled Nuts, Dan Norton in the house. Wonderful. As far as I can tell, I am buffering right now. That is to say, I am looking at my screen here on the YouTube play screen, and I just have a circle. So if you are hearing me, am I buffering? I guess that's my first question. Can you hear me loud and clear? Can you see me loud and clear? If not, I will try to adjust fire. Can you hear or see me? Okay. The second question is, can you hear me? I'm speaking to you. I'm echoing. Okay, thank you. Let me see if I can't fix that as well. I don't know why I would be echoing, but I'm going to try to sort that out. Sorry, guys. Let me try to get things sorted here. Yes, I did say adjust fire. Am I still echoing? Looks and sounds good to me. Thank you, Ava. Okay, if I'm still having audio or video problems, yeah, and Ava says she just refreshed her page. If you need to reload your page, that might clear it. Do I have the speaker up at the computer? No, I do not. And Beth says I'm still echoing. Doggone it. Okay. Let me try something out here, folks. Has this resolved anything? Am I still echoing by any chance? I'm just going to see here. Hopefully we're not going to spend all day troubleshooting problems, but kindly let me know if we are still in fact echoing. Piper Tip says echo still. Well, gosh, folks, I don't know what's going on here. This is... Oh, I see. Hang on. Says, wait a minute. How about now? Does that fix anything? First few times he has always live stream. Eddie would know because he live streams all the time. Are you hearing me now? Am I good to go? Hey Zishan, how you doing, man? There it is. Yeah. Okay. Great. I found that OBS has two microphones listed, and I turned one of them off. All right. Thanks everybody for your patience. I apologize for the confusion. I'm going to go ahead and just quickly refresh my own live stream chat. And I wanted to tell you guys, while I'm doing that, I wanted to tell you about some amazing things that are going on. And then we'll get to some Q&A and stuff like that. But first thing, and I'm actually working on a video about this, but this is such a, for me, I don't know, for me it's a bit of like not just a cool thing, but a pretty inspiring thing, and that is Voyager 2 left, well, I don't want to say it left the solar system, but it is now in interstellar space. And what that means is that it actually crept out of kind of like the sun's protective bubble. There's like this vast, comet-shaped bubble surrounding most of the solar system, and it's called the heliosphere. And the heliosphere is caused by the sun's solar wind. It's blowing out all of these highly charged particles of plasma, and it just blows it all out into space in all directions. But eventually, that plasma that forms this heliosphere around the solar system ends up coming to an abrupt halt. It kind of slams into the interstellar medium, where all of a sudden it's met by incoming particles and winds from other stars and even galactic cosmic rays. And Voyager 2 noticed a sudden drop-off on November 5th. On November 5th, all of a sudden, boom, all of the sun's wind particles disappeared, and all of the interstellar wind particles and cosmic rays suddenly jumped up. Behold, Voyager 2 is now in interstellar space. It is now on its interstellar mission, and it's measuring the environment surrounding our solar system. And this is great because not only did Voyager 2 enter the solar system, but Voyager 1 did the same thing. I'm sorry, not only did Voyager 2 enter interstellar space, but it also is joining its sister ship, Voyager 1, which went interstellar back in 2012. So that's kind of cool, I thought. I'm old enough to remember when Voyager 2 and Voyager 1 were both doing their flybys of the outer solar system, or what we used to think of as the outer solar system. Turns out it's a lot more inner solar system compared to what we've learned is out there since then. But now we have two spacecraft that are, for all intents and purposes, genuinely in interstellar space. However, they are not out of our solar system, which is kind of strange, right? I mean, how can you be in interstellar space yet still be in the solar system? Well, it all has to do with this heliosphere that I was telling you about. Once the heliosphere ends, okay, now you are under the influence, you might say, of the winds and particles from other stars. But you're not out of the solar system, and that's because there are still objects orbiting the sun even at this distance and far beyond. And now we have the outermost regions of the so-called Kuiper Belt. This is a vast swarm of small icy comets that orbit around the sun out past Neptune. And then even beyond that, there is the Oort cloud, which is starts at 1,000 times the distance from the sun to the Earth, or 1,000 astronomical units. So it's really amazing to see this, and it's so great to, this is so cool. I've got a troll. Thank you. Okay, goodbye. And let's see. I think I could put this user in timeout. Yeah, I'm not going to make you a mod. See you later. Okay. So this is great. There must be people who just watch YouTube looking for live streams, and then they come on, and then they just shout insults. So achievement unlocked. Anyway, so now we have there's an Oort cloud, which consists of trillions of comets that are just kind of orbiting the sun very silently, and eventually in about 30,000 years from now, Voyagers 1 and 2 will pass through the Oort cloud, and they will truly have left the solar system. So these spacecraft have about another 30,000 years to go before they are actually legitimately outside of the solar system entirely. However, they are yet in interstellar space, and now they're telling us what the environment around the sun is like. It's kind of cool, It's neat to see, and I got a big kick out of that. Not only that, but speaking of the outer reaches of the solar system, the astronomers who are searching for Planet 9 just wrapped up a 7-night observing run atop of Mauna Kea, Hawaii, and they got a lot of data. I mean, this was actually a really good observing run, probably their best observing run that they've had looking for this thing. Which this means that they're able to pretty much spend the next few weeks just going through all of the images that they collected of the sky, looking for something that's moving. And if they can find something that appears to move, they'll try to work out its distance, and from there, try to work out its orbit around the sun. And if it is what they expect, and if it's as far as what they're expecting, and if it's taking the orbit they're expecting, they'll come out and they'll declare that they've discovered Planet 9. Just how amazingly cool is that? They may not. I mean, there's lots of reasons why they may not, but there's some really exciting prospects going on right now. And then much closer to home, we've got the Parker Solar Probe that is about to enter into the sun's outer atmosphere. When I say about to enter, I mean in about 7 years. Okay, this is nothing that's going to happen anytime quickly, but it's already made its first orbit around the sun, and with every passing orbit, it's going to come closer and closer and closer until it finally passes through the sun's outer atmosphere. That's going to begin in about 7 years. So this is kind of cool. We've got, a spacecraft like that's about to kiss the sun, and we have two other spacecraft that have left the influence of the sun. Hey, well, not bad, right? We're covering both ends of the solar system, and that's just what's going on in our solar system. Oh man, it's hard to stay on top of all this stuff. But anyway, I digress and I ramble. It's great to see you all here. Thank you so much for dropping by. This is so exciting. 25 people are watching. Wow, biggest live stream I think I've ever had. Neato, thanks. So if you have any questions or anything like that, please feel free to drop them into the chat because I want to help you understand what's going on. And particularly if you're one of my students and you're planning on taking my final exam tomorrow, or if you'd like to show up and maybe try out the final exam. If you have any questions about anything that's going to be on the test, they're fair game. And I will say that my students are going to get top priority just because their test is coming up tomorrow. And then others are going to be taking their finals on, my other class is going to be taking their finals on Monday. So that was the main motivation for today's little gathering here. So how is everybody doing? Let me just quickly go through and just take a look in the chat. I just want to say welcome a few more folks here. We have Modern Day Family Man. Hey, Eddie, how you doing? Harley, Beth, Boiled Nuts is here. Oh my gosh. Vault Dueller. Hey, thank you. Vault says throwing random insults ain't trolling. No, I don't know. Maybe it's not trolling. But it's not nice. I kind of have like this whole sort of predisposition to being kind. Modern Day Family Man, Launchpad Astronomy, can I have the answer to question 5? You know what? You're not even enrolled in my class. So yeah, I'll give it to you. Now, if you're one of my students, just, don't listen, okay? But the answer to question 5 is D. Why not, right? No, the answer to question 5, it has to do with seasons. What would happen if Earth did not have an axial tilt? Okay, if it had no axial tilt, it's going around the sun like this, tilted by about 23.5 degrees, what would happen if the axial tilt were like this? And the Earth was just going around? Well, the answer is there would be no seasons whatsoever. And that's because all of our seasons are the result of the axial tilt. We have the Earth when the Earth is, if this is our sun and this is the Earth, sometimes when the northern hemisphere is leaning toward the sun, we're getting more direct sunlight, and therefore we have longer days, and the sunlight that we get is more direct, so we have more efficient heating of the ground, hence we call it summer. Meanwhile, the folks in the southern hemisphere are kind of leaning away from the sun, and their sun angle is a lot shallower, so they're getting less direct sunlight. They call it winter. However, right now we are approaching December 21st. We will soon be at what we call the winter solstice, where the North Pole is, where the northern hemisphere is leaning away from the sun, and now we are the ones receiving much less direct sunlight. maybe I've got my light over here. I don't know if it works to do this way, but if my light over here is the sun angle is a lot more shallow, and we're just going to get much less sunlight. Not only that, but the sun rises farthest in the southeast, and it sets in the southwest, so it's not up for very long, so we get fewer hours of daylight. Not enough time to cook under the sun. So what would happen if the Earth had no axial tilt? Well, both hemispheres would receive equal amounts of sunlight. It would be spring or autumn, however you want to think of it, all year long. There would be no seasonal changes. So everybody likes to say fill in the blank is the reason for the season. Axial tilt is the reason for all the seasons. Okay, so I hope that helps. Let's see. Hey, Peter Quinn, how you doing? Let me see if I can find some other questions. Okay. Ava says, oh, I already remember that one. Yeah, that's cool. Awesome. Yeah, I think you got this one, Ava. Let's see. Yeah, Zishan, there you go. See, it pays to show up for review. Kevin and Jamie Lannister say hi. Well, thank you very much, Kevin and Jamie. All I could say, man, is sorry about that hand, dude. That's gotta hurt. Okay. Let's see. Well, Vault asks, wondering how long it takes from the moment when Planet 9 is found and that information gets to the public and everyone gets to know about it. Or does it take forever to confirm that information? Well, actually, no. Based upon what Mike Brown was tweeting, he did a lot of really interesting tweets this last week during the observing run because he had to do something to stay awake, all night long. And he said that, no, they would pretty much announce it right away. I mean, if they were confident in their findings, they would go ahead and make a press announcement, which is a little bit gutsy to do because in science we have what's called a peer review. In other words, we write paper, we do our research, we write papers, we perform our analysis, we come to our conclusions, we write that all out in a paper, and before it gets published in professional journals, it is sent off to somebody else, preferably a peer within our field, and they'll review it, just try to make sure it makes sense and that there's no glaring obvious questions that are left unanswered. And if it passes the so-called peer review, it gets published. But Mike Brown said pretty much that they would announce it right away if they were confident, if they had a high degree of confidence, because they know exactly what they're looking for. And so, yeah, I would say that, let me put it this way. If they found, if Planet 9 were in fact detected in this past week's observing run, they'll go ahead and we should expect to hear an announcement sometime as early as January. If they don't find it, or if they're not sure if they found it, they have another observing run coming up in February. So, yeah, it'll be pretty quick. Let's see. Oh boy, what do we got here? So how long? Oh, Jim Barley asks, yeah, how long does it take for signals to and from Voyager 2? Yeah, it's a really good question, Jim, because the farther away Voyager 2, well, either of those spacecraft are, the longer it takes. And the short answer is, let me think here for a second. They are, well, I should be able to calculate that right now. Let's see here. Speed of light is what, 300,000 kilometers per second, right? And Voyager 2 is at about 122 astronomical units. 1 astronomical unit is, my students know this, how big's an astronomical unit, guys? 150 million kilometers. Well done, right? So it's 150 million kilometers. And you're going, let's see, 150 million, so let's do this. 150 million, 150 times 120 astronomical units. Okay, so that puts Voyager 2 at about 18 billion kilometers, if I'm doing my math right here. And if we divide that by 300,000 kilometers per second, that's 60,000 seconds. All right, so it takes 60,000 seconds for the signal to come back from, let's say, Voyager 2. And let's see, how many seconds are there in an hour? My students know this. 3,600 seconds, right? So it takes a signal from Voyager 2, 16.666, etc., basically a little less than 17 hours to travel from that distance to Earth. Okay, so that's how long it takes. Yeah, it takes let's see, Piper took a good chunk of the day. I think I may be off by 1 kilometer. Eddie, man, I don't need this from you, pal. This is abuse. I'm blocking you right now. I'm just kidding. Let's see. So yeah, we are talking about a 17-hour one-way trip just from Voyager 2. Voyager 1's even farther away. But here's the other thing though, because Voyager 1, Voyager 1 is, I'm going to talk about this in my video, but I'm sorry, both Voyagers are powered by radioisotope thermal generators, which is just a nice fancy way of saying it's a hunk of uranium that's decaying. And as the uranium decays, it gives off heat, which can then be used to power up the instruments. Well, the radioactive plutonium's been decaying ever since it was launched in 1977. That means that it's losing about 4 watts worth of power every single year. Currently, the Voyagers transmit at something like 20 watts. Now, how much is 20 watts? Well, 20 watts is about the same brightness or the same luminosity as your refrigerator's light bulb. So there's a refrigerator light bulb's worth of power coming out of the Voyager transmitter, and by the time it crosses those 17 light hours to get to Earth, 18 billion kilometers, its power has weakened to about I think it's like 1/10 trillionth of a billionth of a watt. Extremely weak signal. And that's why we have these really enormous radio dishes that are just, we've actually made them bigger over time to collect that very weak, feeble signal. And yet encoded within that very weak signal is now information about the interstellar medium beyond the sun, which is kind of cool. Okay, long answer to a question, but Linda, Eddie, that was my husband's questions. Good, I'm glad we were able to do that. Jerry says plutonium. Did I say uranium, Jerry? If I did, you are correct. I really did mean to say plutonium. It's just one of those radioactive things that I try to stay away from them because they're kind of dangerous. Okay. Peter Quinn asks, will Voyager 1 or 2 still be able to contact us when it reaches the outside of the Oort cloud? No, it won't. And it's not because it'll be too far away, but because both spacecraft will have long run out of power by then. The Oort cloud begins at about 1,000 astronomical units. And it will take, even though both spacecraft are racing out there at speeds of something like 60,000 kilometers per hour, or, if you prefer, I guess that's about 50 million miles an hour or something like that. I'm doing my conversion wrong, but anyway, it's fast, right? Even at this rate of speed, they're not even going to approach the inner edge of this Oort cloud for another 300 years. And then they'll need about another 30,000 years before they emerge from the other side. So the spacecraft are both losing power at a rate of about 4 watts per year. Right now, the mission managers would just love it if they could make it to 2027, because that means that the Voyagers will have been operational for 50 years. Yeah, that's an amazing achievement. They're already the longest serving spacecraft ever. But, hey, what do you know? I mean, so these things are going to be dead long before they even come close to the Oort cloud. Yeah, and by 2025, the Voyagers won't have enough power left to communicate with us. That's kind of the expectation, but the mission managers really want to hit 2027. They may turn off everything except for, the computer and the transmitter just to get a signal 50 years on. That's what they would like to be able to do, but we'll see. Let's see. Peter Quinn, it's been in space longer than a year longer than I've been here. Good for you, Peter. You're just a baby. Okay. Anyway. Yeah, 41 years. Is that amazing? It's pretty cool. So let's see. Gosh, what else is going on? So what else you guys want to talk about? Students, you got anything for me? Anything I can help you with? Make sure you ask. Don't be shy. Just feel free to throw a question in there. Speaking of questions, I thought I saw another one. Ava asks, how do you calculate brightness and luminosity if you are given the distance of stars? Okay, well, that's a really good question. There's actually not a very difficult calculation if you know what the distances are, but it's usually easier to work it if it's usually easier to figure out the distance if you know what the brightnesses are. So let me try to just sort of talk through this a little bit, just kind of hand wavy. But what we have is an equation that relates the brightnesses. We measure brightnesses using something called magnitudes, right? So the higher the number of magnitude, in other words, a magnitude 5 star is about 100 times fainter than a magnitude 0 star. Okay, so it's kind of weird when you think about it, but if you kind of look at it this way, if the first star that comes out tonight is the first star that you see, that is called magnitude 1. The second stars are magnitude 2, and so forth all the way down. So the higher the magnitude, the fainter the star. So if you know a star's distance, and if you know something called its absolute magnitude, or excuse me, if you know its magnitude, okay, its apparent magnitude, and you know its distance, and you know what type of star it is, you can work out what its intrinsic brightness or its luminosity is. And from there, you can, you could solve for that. Or if you know a star's apparent magnitude, you measure that. And if you know what its intrinsic luminosity really is, what its true brightness is, you can compare the two, and that will give you the distance. So there's a few different ways to solve that equation. Let's see. And Ava, let me know if I didn't answer your question correctly. I want to make sure I understood it, let alone asked it correctly. RPM Nexus, how you doing, man? Good to see you. Let's see. Okay, Paul Singh asks, are any secrets that you have that we can use to prepare well for the exam? You're here. I don't know. I hope this helps. As far as secrets that I have, I don't really have any secrets. I don't think I've held anything back from you except what the questions are. I would say this: if this helps you at all, I'll be asking some questions. I happen to have the exam here right now, so if you're watching the students, maybe make a couple notes here. I'm going to be asking questions that will cover, the sky, right? What we learned, a little bit about what we learned about the sky, how it works over the course of a night. How the sun appears to move around the sky over the course of a year. I'll be asking about the seasons as well. We talked about that just a little bit ago. I'll also probably ask you a question or two about the moon and its phases, right? So try to understand what causes them and what they are expected to be at given times. You might want to think a little bit about eclipses and how they work, both lunar and solar. Oh, let's see. As far as, remembering Kepler's laws of planetary motion, and I saw a question about Kepler's third law, which I'll come back to in a moment, and I'll talk about that. We also you might want to also brush up on your gravity. Make sure you understand how gravity works, particularly Newton's laws of universal gravitation. Understanding tidal forces is good. A little bit about telescopes here and there wouldn't hurt. Also, perhaps understanding the properties of light, and think about what happens when things move away from us or move toward us. Try to brush up on your Doppler shifts. Let's see. You might also want to think about the colors of stars and what that tells us about how color is related to temperature, right? So we learned about Wien's law. We learned about Planck curves. Might want to review that as well. Also might want to consider things about planetary atmospheres, particularly how Earth's atmosphere compares to Venus's and to Mars. Okay, what's similar about them? What's different? You might also want to know a little bit about the moons of the outer solar system. Just what are their general properties? What distinguishes different types of moons? How do we consider moons? There's really two ways, right? Based upon their origin and based upon their geological makeup, right? So think a little bit about those. Might also want to review ring systems, understand how those work. And don't forget, of course, our solar system star, the sun. Think about how that works. Think about why it shines, how it shines, and some of the things that goes on around it. You might also want to review, things like, we talked about exoplanets. Might want to take a look at those as well and try to understand what it is we meant by habitable zones around stars, and are they really habitable? Okay, I think I gave you a few hints there as to what's going to be on the final tomorrow. This is why you show up for these live streams, I guess, right? So I hope that can help you. Peter, exams, yeah. So again, this is just for my students. This is not for everybody else. But Paul, I hope that helped you out there. Zishan asks, could you explain Kepler's third law, sorry? Sorry what? That's right. That's sorry because you're a student of mine and I've explained this to you 100 different times. Oh, I kid. Okay. So Kepler's third law. Let me see if I can do something here with you guys. I want to try to show you guys something. I'm going to move some screens around. I apologize for the mess. I will try to get this up and displaying on screen for you as quickly as possible. But what I'd like to do, I'm going to try to move this over here. But what I'd like to do is bring up my keynote. And I'll try to, I realize I've been telling and I would much rather be showing you guys because this could be a little bit easier to understand. So let me try to bring up my slide deck here. And I'm not going to go through a whole lecture on you guys. No, I'm just going to show you just some relevant concepts. Again, it's always easier to show than to tell. So talk amongst yourselves. And of course, Keynote is just taking its own time. Let's see. Let me close down some windows here. Okay, well, while my computer's thinking about opening up my window. Oh yeah, thank you for the tree. Appreciate that. Yeah, funny thing, I spent about a week trying to get that thing to work. I had to repair a bunch of lights. I'm just glad it's up and running. Okay, so let me bring up. Let me try to bring up my slide deck. It's taking some time to think about it. Let me just double check on. Oh, Ava asks, anything we should not study? I would say. Let me think about this for a second. I mean, one thing I will say just in general about the final exam, my philosophy on final exams is that, during the other exams that we took, by the way, for those of you who are not in my class, I like to call them celebrations of knowledge. Just sounds nicer. Celebrate your knowledge. Anyway, whenever we've had our celebrations of knowledge, I've tried to keep them, pretty focused on what we talked about in class and kind of went a little bit deep. My philosophy on the final, on the other hand, is that, well, now we're going to take a broad look across, just everything we learned, a sampling from all around the semester. So that's going to be, if the celebrations were narrow and deep-ish, the final is broad and shallow. Does that make sense? So it's not intended to be this, real head scratcher. I can say that as far as topics that you should not study, I don't think there's anything I know there's nothing on the final that we didn't talk about in class, and that's the first order of business. I don't think I'm going to be asking a whole lot about planetary formation or anything like that. I may have like one question on it, but there won't be a whole lot. I know we talked in depth about the formation of planetary systems and extrasolar planets. However, for the final, I think it's going to be more weighted toward the topics that I talked about before, which is essentially the sky, gravity, light, and the solar system. So anyway, so what else can I talk to you guys about? And if you're not in my class, please feel free to throw a question in there. I am not worried about, I'm not exclusive to just my students, but they get top priority. They always get top priority. And I do apologize for trying to multitask here. I'm not doing a very good job of it. But wouldn't you know it, it's I'm trying to. I have to download this stupid. I have to download this dumb thing because iCloud stores everything for me, and that's fine until I actually need to access the damned file. Then it takes forever. Ava asks, how many questions are on the final? Oh, I think it's like around 40 or so. It shouldn't take you too long to knock it out. All right. Well, I hate being on live streams where it's just dead silence. Let me tell you. Oh, and Discord gets priority. That's right. I have a Discord channel. I forgot. Yes, I do have a Discord channel. If you are on, you know what I'll do? If you'd like to catch up to me on Discord, it's a real mess right now. I'm still barely setting it up. But here is a link to my Discord channel. There I go. I just put that in the chat, and you're welcome to join me on Discord. So Piper Trip asks, can I talk a little bit about color index and how it's measured in practice? Yeah, sure. I'd be happy to, assuming I can actually get the thing to open up. But I might actually have a way. I think I have a way of showing that to you. Let me see if I can bring that up for us. Now, I do apologize for the delay here, but I do have something that's opening up. It might, in fact, work. We will see. I should quiz you. Oh, man. Okay, yeah, you know what? We're going to play... Oh, wow. Okay, to quiz you guys. First of all, let me lower my volume. I apologize for talking too loud here. Let's see. I'm going to ask you guys a question. What is... okay, so... which types of planets would have formed in the outer solar system beyond the frost line? Would they be A, terrestrial planets, B, giant planets, or C, dwarf planets? Which type of planets formed beyond the solar systems or beyond the early solar system's frost line? Terrestrial planets, giant planets, or dwarf planets? Go. Let's see what you guys all think. Okay, we have gas giants, we have dwarf. And, there's some subtleties to this question, but it seems like people are saying dwarf. Alt says, okay, giant for modern day family man. Not a student, but love this. Thank you. Okay. Frosty planets. Yeah, they're gonna be frosty, all right. So the types of planets that are likely to form beyond the frost line are going to be the giant planets mostly. Which is not to say that there aren't dwarf planets beyond the frost line. There are. But they are planets. There's at least one dwarf planet in the asteroid belt, which is inside the frost line. The giants form outside the frost line. So what is the frost line? Well, the frost line is basically just that distance where not only do you have like grains of silicates and, you know, what are called refractory materials, but you also have not only those, but you also have volatiles. You have water, you have ammonia, you have methane, especially in the farther out of the solar system. And that makes sense because the farther away you are, the colder it is, and therefore the more materials you have to work with. Water condenses, ammonia condenses, methane condenses, all that stuff condenses. So you can form very, very, very big planets. That's why you get giant planets in the outer solar system. Okay, now someone was asking about color index. I think I can finally show this to you. Let me see if this will work. Gosh, I hope so. Nothing like I love trying out technology when I really have no idea if it's actually going to work, but I'm going to try to run this keynote presentation. I'm probably going to just destroy my computer. And I also know, let me do something here. Okay, so what have I done? What am I doing? So I'm going to try to bring up, I'm going to try to bring this up over here. Okay, I'm going to bring this up over here, and I'm going to show you my other screen. Hey everybody, am I back? Can you hear me now? Can you hear me now? So my sound cut out when I switched screens. How about now? Okay, so Paul says he could hear me. All right, I'm going to try this a different way. We're going to make it work. Going to keep working this until we get it right, guys. All right, do you still hear me? Do you still hear me? I'm very low. Can you hear me now? Can you hear me better now? Let me see. I hope you guys can hear me. I heard that I'm very quiet. It's like trying to talk to my mom, okay? Let's see. Okay, I hear a yes. I hear I. Better. Okay, cool. Love lunch bag astronomy. This is what makes him awesome. Well, thank you very much, Vault. Gosh, I sure don't know why I can't. So it doesn't seem. And now are you seeing? Are you now seeing my my slide, my window? That's gonna work. Okay, please tell me you can hear me as well as see my slide. Okay, I hear yep. All right, tell me, give me hashtag here, hashtag slide, loud and clear, slides. Okay, cool. All right, great. All right, yay, it's working. Cool. So the question was about color index. Well, here's how color index works. Okay, we have on the right-hand side, we have Orion. We have two stars, right? Betelgeuse and Rigel. Now the thing is that if we were to take a look at these two stars, okay, we have magnitudes, right? So Betelgeuse has a given magnitude in the visible part of the spectrum, as does Rigel. So let's take a look at Betelgeuse, but this time we're going to put a blue filter in front of Betelgeuse. In other words, we're going to put a blue filter between our telescope camera and the star. And when we do that, we measure its magnitude, which is essentially a measure of its brightness. So we say that, okay, its magnitude in blue is a positive value, it's 2.35. But if we switch to like a yellow filter, which is essentially the middle of the visible part of the spectrum, it gets a new magnitude. It becomes a bit fainter. I'm sorry, it becomes a bit brighter, excuse me. It's now 0.05 or 0.5. And remember, the smaller the number or the lower the number, the brighter it is. So if we subtract these two values from another, if we subtract the visible from the blue, you get 1.85. So, all right, so far so good. It's a number, some indicator of something, right? So let's find out what we're indicating. Let's take a look now at Rigel. We're going to perform the exact same experiment. We're going to put a blue filter in front of Rigel, and we're going to get a magnitude that's very low and therefore very bright. It's 0.09. But if we switch to the yellow filter, it's still brighter than Betelgeuse, but it's fainter than it was in blue. So now it's 0.12. So if we subtract the visible from the blue for Rigel, we get a negative value, minus 0.03. Everybody cool so far? So what is this telling us? Well, this is telling us that, the lower the value, right, the bluer the star, and therefore the hotter the star is. So by comparing magnitudes in different filters, we can really just take the temperature of a star. We can measure its blueness or lack thereof, and the bluer the hotter, and the redder the cooler. So that's how you measure temperatures of stars. I hope that works. I hope you guys caught that. I saw a comment there saying we have just witnessed Keynote destroying your computer. Yeah, I hear you. All right, let's see if that worked. I hope that did. I'm going to try to come back over here. Can you all see me now? Okay, so that is an example of how I teach my classes. My students are probably sick to death of hearing this, but there it is. I'm still waiting, by the way, on that Kepler slide deck to download, because I really do want to answer your question, Paul. And Paul, I have that up for you right now. So a couple of questions were being asked about Kepler's laws of motion. I'm going to attempt to bring that up as well and attempt to show that to you. But while we're waiting for the computer to think about stuff, by the way, students, do not do anything about this. But for everybody else watching, did I mention I'm on Patreon now? And I really need to buy a new laptop. I kid. All right, except I'm not. Anyway, I'm going to go ahead and bring up this slide deck. First I'm going to do is I'm going to transition over here to this screen. And I'm going to attempt to, I'm going to ask you guys if you can see anything as well as hear anything. We had it and we lost it. Try again. Wow. Okay. Huh. Weird Heather, wow, this is a smart stream. I feel like I'm at a university lecture. Yeah, it's just, there's a reason why I don't actually teach my class online. All right. I hope you can all see this, but please let me know if you're not seeing it. But a question was asked about Kepler's third law. Okay. And hopefully you're seeing it now, and hopefully you're still hearing it now. But Kepler's third law works like this. In this case, we have the Earth, and it's in orbit around the sun. Now, this is really exaggerated, but basically Earth orbits the sun in an ellipse, like you see here. And what's going to happen is that Johann Kepler worked out this really cool relationship that you see here. He found out that the orbit of a planet or rather its orbital period, represented by the letter P in this equation underneath Kepler's third law, if you take the orbital period and you measure it in years, and if you square it, it turns out to be exactly equal to the cube of its semi-major axis, represented by the letter A. So let me show you what I mean. If we take Earth around this, consider Earth going around the sun, okay? If you consider Earth going around the sun, all right, well, it has an orbital period of 1 year, obviously, right? That's how long it takes for the Earth to go around the sun. But it also has a semi-major axis, or an average orbital distance of 1 AU. So if you look in the lower right where you see this value for the orbital period is 1 year, the semi-major axis is 1 year. So if we take the orbital period and we square it, we get 1 squared, which is equal to 1, and we take the semi-major axis and we cube it, and 1 cubed is equal to 1. Okay, that's not very exciting, I know, but now let's just consider another planet, right? Let's consider Jupiter. Well, Jupiter has an orbital period of 11.9 years. That's how long it takes to go around the sun, but it has a semi-major axis of a little over 5 astronomical units, right? So 1 astronomical unit is the Earth-Sun distance, so Jupiter's 5.2 times as far away. Let's go ahead and take the value of Jupiter's orbital period and let's square it. Well, we end up with 141. But if we take this value, 5.2 astronomical units, and we cube it, we get, boom, 141, right? So for every planet going around the sun, all you have to do is know what is its semi-major axis and its orbital period, and if you cube the semi-major axis, it'll be equal to the square of the orbital period. So orbital period squared is equal to its semi-major axis cubed, and that's Kepler's third law of motion. All right, so let me see. Did I answer that question, Paul? I hope I did. Please let me know if it's still not coming through. And I'm just going to kind of scroll through here and just double check to make sure I didn't miss any questions. You guys have been so patient. I really appreciate all this, and I don't know about you, but I'm having fun even though I'm kind of pulling my hair out on this. Okay, Paul says yes. All right, good man, Paul. Proud of you, man. That's fantastic. So let's see. We've got, let's see. Working on one screen, taking a test on another screen, listening to Christian in the background, busy. Good job, Eddie. Appreciate it, man. That's fantastic. Okay, Betelgeuse. No, we just need to find a habitable planet in proof of sandworms. Yeah, I'd say that's not a bad idea. You know, I don't know what I would do with a sandworm, but you know, that's just me. All right. Well, what else do we have, ladies and gentlemen, that we can talk about? You know, I know something that I wanted. I'm really excited. Oh boy. Let's see. So all right, so guys, based upon this, I have a question for you. Suppose we discover a new planet in the solar system that's at 2 astronomical units. In other words, it's twice as far from the sun as Earth. Don't ask me how we didn't know about it, but there it is, right? It's out there. So is its orbital period going to be shorter than Earth's, or is it going to be longer than Earth's? In other words, will its orbit take longer or less time than Earth does? So what do you think? That's my question for you. Will it be longer than Earth or shorter than Earth? Remember, its semi-major axis or distance is 2 astronomical units. Gonna wait for you guys to respond. This is my quiz for you guys. What's it gonna be? Greater than 1 year or less than 1 year? Okay, we have one saying 2 AU. It should take longer. Jerry says longer. Let's see, any other guts? Compared to Earth? Yes. What does that mean, Vault? Compared to Earth, yes. Would it be longer or shorter than 1 year? Answer, I agree. Okay, good. Okay, little cripple, longer. All right. So far, the consensus appears to be longer, and indeed that is correct. It would be longer. How much longer? Well, no problem. I mean, we can calculate that, right? Let's see. What is 2? Let's see. Its semi-major axis would be 2 AU, right? So what's 2 cubed? Anybody know? What is 2 cubed? 2 times 2 is 4. 4 times 2 is, come on, 16, right? Cool. So what is the square root of 16, right? So let's bring up our calculator here, because I can't do math in my head either. I'm pretty bad at it, but that's okay. That's what the good Lord gave us calculators for, right? At least I thought it gave us calculators for that purpose, but that's okay. All right, here we go. So if we're going to take 2 astronomical units, right, and we cube it, okay, so we cube it. Oh, 4 times 2. Did I say? Oh, 4 times 2 is not 16. It's 8. Oh, gosh, man. Come on, guys. Help me out here. All right, what's the square root of 8? 2.8, right? So it would be it would have an orbital period of 2.83 years. So yeah, it would definitely be longer. It would be nearly 3 years long. 8, not 16. Yeah, I know. Ask questions. I got you. I told you, man. Math was never my strong suit. That's why I went into astrophysics. Okay, I mean, geez. All right, we're back. Cool. And if you're a student of mine, you probably have some idea of a question I might ask on tomorrow's final. You never know. I'm just saying. I may ask that question. I may not, but I probably will. And that's my nice way of saying it's on the test. But I'm not going to make you do the math, because don't worry about it. I don't want you to not get the question right because of some stupid math error. Let's see. You know what else is really exciting that's going on that I almost forgot to mention, but I'm sure you all heard about it. It's the InSight lander, right? That landed on Mars, and it's going to do something that's never been done before. And it's actually going to be measuring the interior of Mars. It's listening for Mars quakes. It's trying to figure out what is going on inside the planet, because we don't know for sure whether or not Mars has. And I'm probably echoing, and if I am, I apologize. I'm going to go ahead and try to kill that out. Okay. We've been saying for years that we don't believe Mars has any internal heat left. I mean, everything that we have on Earth, all the geology, all of the volcanism, the earthquakes, everything is all due to heat trying to escape the interior of the Earth. That drives convection, and that drives plate tectonics, right? The Earth's surface is cracked into these huge tectonic plates that are kind of moving around on this mantle of lava and magma. Mars, on the other hand, does not have a fractured, plate-like surface like we do. But it does have evidence of previous geology. I mean, there are volcanoes on Mars, right? They're extinct now, but they're there. There's also Valles Marineris, this enormous rift valley that's as large across as the United States, right? It's a huge rift valley. The thing is that there hasn't been anything happening on Mars lately from a geologic standpoint. In other words, all the volcanoes are extinct. We don't think there are any severe Mars quakes going on, but we don't know. So Mars InSight has landed. It landed on the planet, I think it was about 2 weeks ago, or it was a week ago Monday, and it's actually listening. It's going to set what is effectively a seismometer, right, on the surface of Mars. It's essentially just going to be listening for Mars quakes. Now, these quakes may come as the result of some, heat that is still remaining inside the planet. Maybe it eventually will manifest itself in a minor Mars quake. Or more likely, what's going to happen is that asteroids are going to impact Mars, and they're going to form craters. And when they do, the planet's going to ring like a bell. And, well, actually, they're going to see, does it ring like a bell, or does it ring like a rock? How does it ring when an asteroid hits it? And it's going to be sensing those vibrations, essentially just measuring seismology to see what the interior of Mars is like. And that's really exciting, because it's very likely that I'll end up having to rewrite my whole class on Mars, and then everybody in the stream who took the class, I'll have to go back and change all of their test answers, and they'll probably have to come back and take the class a second time. But this second time, they will know for sure how Mars works on the inside. Huh? Okay, so yeah, there you go. Ask questions, try stuff. Math was never my strong suit either, so I quit photography and started mechanical engineering. There you go, mechanical engineering. I love it. Let's see. Paul saying, what else is on the test? Oh, yeah. Okay, Paul. All the things. Yeah, all the things. All right. And do I remember correct that some time ago Mars has cloud from volcano? Does Mars have cloud from volcano? I'm not sure what you meant by that, except that clouds have been. Well, maybe I think I do. Yes. The short answer is yes. Mars does occasionally form clouds. Okay. By the way, Mars is an extremely thin atmosphere, right? It's very low density atmosphere. So the clouds that do form, they're kind of few and far between sometimes. But yeah, occasionally ice crystals will form in the uppermost part of the atmosphere around the volcanoes, just like they do here on Earth for that matter. And yeah, Olympus Mons on Mars has found, we've seen cloud kind of collecting around the volcano tops. So yeah, Mars does have clouds, and occasionally they do gather at volcanoes. It's called Olympus Mons, Peter, and Olympus Mons is the largest volcano in the solar system. And by the way, there's a reason for that. I don't know if I can bring it up here or not, but I'll attempt to, because this is something else my students might find useful for tomorrow, assuming I can. Let's see here. Aha. And I know we're getting on to 1 o'clock here. I didn't have an official cutoff time, but I was thinking about an hour. But if you have more questions, I'm more than happy to stick around and answer them. But let me show you this one thing about Mars that I think is really interesting, particularly around this massive volcano. What you have here is, assuming it comes up here. Here we go. And please let me know if you're having difficulty seeing anything. Well, I'm just waiting for my Keynote to get its act together. It's funny, I bring up Keynote and then it just stops. And it's really strange. But let me try again. Because we're fearless here at Launchpad Astronomy. Please let me know. Take care, Piper Trip. Nice to see you. Ava, sure, I'll give you another quiz question. Okay, so please let me know if you can see my screen. I should have an image of Olympus Mons on Mars. This is huge. This is, in fact, about the size of Arizona. So what you're looking at right now is a gigantic, what's called a shield volcano. And at the very top are these craters. This is called the caldera, which is basically just the collapsed top of a volcano after it goes extinct. But if you look, by the way, did I switch over to my, no, I did not. I guess. Okay, you should be able to hear me now. And I will now try to bring up, gosh, what is with Keynote? Why does Keynote kill audio? Okay, my sound has dropped when I switch screens. Please do tell me if you can hear me now. Can you hear me now? Yes, we hear you. Do you see Olympus Mons as well as hear me? Good now? Okay, great. All right, cool. So, loud and clear again. Yay. Yeah, it's so freaking easy. All right. So Olympus Mons, this is a huge shield volcano, and again, you can see that there's this big region here called a caldera. This is basically the collapsed what used to be a gaping hole that when this volcano was erupting. You can even see how the lava effectively has kind of, flown downhill and smoothed over whatever craters may have formed. But if you look closely, you'll see that there are these two craters, and they have these really well-defined rims, these really well-defined edges. So what that tells us is that these craters are impact craters. Okay, they came from, asteroids, meteorites that came in from outer space. They fell on Olympus Mons, they smashed in, and there has not been any eruptions since that would otherwise fill in these craters. So this tells us that this volcano is extinct and has been extinct for some time, even though it's huge, right? It's the size of Arizona. But if we were to look at this sideways, okay, so here is that same that same Olympus Mons taken from the same spacecraft, except rearranged in a computer to give us this 3D perspective. And we can compare that down here to planet Earth, right? So here we have sea level. Here we have Mauna Kea, which is 14,000 feet. Here we have the peak of Mount Everest, which is higher. I think it's, 33,000 feet, if I remember correctly. And this is the peak of Olympus Mons. So when I compare this to this, and this is Mount Everest, and this is Olympus Mons, and this is Mount Everest. I'm just checking here, but Olympus Mons seems a lot bigger than Mount Everest. Okay, it's huge, right? So my question for you, my friends and students, why or how is it that Mars can have such enormous volcanoes? There are two reasons, right? There are two reasons that cause Mars to have it. And I'll give you a hint. Mars is smaller than Earth, okay? And I've already given you another hint because we talked about what drives, let me give you another hint. Why aren't the mountains bigger on Earth? Well, part of it is because we have plate tectonics, right? These mountains are sliding around on these gigantic tectonic plates, and when they collide, they grind into each other, they can tear mountains down. So my question for you is, why is it that Mars can have these ginormous volcanoes? Okay, so I'm seeing weaker gravity. Yeah, okay, good. I see lower gravity and thin atmosphere, lower gravity and less erosion. Okay, great. Lack of weathering. It is true. Ask questions. There is a lack of weather, right? The atmosphere is a lot thinner, so there is not that much, weather activity that can naturally erode it. But, and here's the key thing. Weather is not preventing Mount Everest from growing bigger either. So obviously weaker gravity. I'll tell you right now, you guys are on the right track. Weaker gravity is part of it. The second reason is because Mars has ego issues? Yeah, Mars has got something to prove, right? Earth has bigger moon. It does, but that's not the reason why. Something else unrelated? Yes, it's something else unrelated. That's something else that's unrelated. Wait. Volcanoes don't move off hot spots. Okay, Jerry, you're on the right track, and Peter, boom, nailed it. Tectonics, specifically plate tectonics, right? So Mount Everest and these guys are on these gigantic continental tectonic plates that are sliding around on top of an underground sea of magma, right, in the mantle, which is actually below the bottom of the ocean. And these plates slam into one another, and they can grind those mountains down. But Mars doesn't have plate tectonics. The surface is solid, it's continuous. So there's no grinding down of mountains, and you have a weaker gravity field. So these things get huge, right? So you end up with, ultimately you end up with low surface gravity and no plate tectonics. It wasn't ego, but you never know, right? Let me just make sure I didn't miss a question. Okay, so I got a couple questions from Ask Questions, Try Stuff. By the way, I love your YouTube channel name, Ask Questions, Try Stuff. Isn't that the best way to go about life in general? Let's see. Isn't there a bigger mountain slash volcano under Earth's ocean that's 2 or 3 times the size of Mount Everest, but we don't think about it since it's under the ocean? You know what? I honestly don't know. That's a very interesting question. I would have to double check. Let's see. Any other questions? Students, anything else I can do for my students in particular before we wrap up here? Okay, all right, let me see. Okay, another question. I'm going to go ahead, switch back over to my camera here. And we're back. All right, let me see if I can... Am I back? I should be back. Let me kill this extra sound source so that I'm not echoing. Okay, so Zishan asks, do aliens exist? I don't know. We really don't know. We'd like to think they do, but we don't know. But there is a place, and also when we talk about aliens, everything is fair game, right? Everything from, Vulcans all the way down to microbes, right? We don't know if even so much as a single-celled organism is alive elsewhere in the universe other than on Earth. It's the only example of a planet where we know where life exists. But there are reasons to believe that life may exist elsewhere, not just in the universe, but even right here in our own solar system. Obviously, Mars is one possible place. There could be, underground oceans maybe of liquid water, and maybe there's some heat down there, which would give, life a source of water and energy. Or there's another place in our solar system, actually a couple of other places in our solar system where we think life may exist. And believe it or not, it's not on Earth or Mars. It would actually be in the outer solar system, underneath the moons of Jupiter and Saturn. So inside the moons, there are these moons are covered in liquid water ice, but they have these outbursts, of gas that is basically frozen water, right? Or actually liquid water that is blasting out into space and is sublimating away into a gas. So that tells us that there must be liquid water, right? If there's heat and there's ice, heat and ice make liquid water. So that tells us there must be a liquid ocean underneath the surfaces of these moons. And if there's liquid water and there's heat and there's carbon for organics and molecules, things like that, organic molecules, that's the ingredients for life. Okay, those are the 3 main ingredients of life. You need a source of energy, right? Which is food. Okay, you need water to carry out those biological chemical reactions, and you need organics or carbon compounds to assemble the building blocks of life, and then you need Wi-Fi. Okay, so if you have those 4 things, right? You can have technically you don't need Wi-Fi, but it's kind of important. Anyway, if you have those things, then you've got the ingredients for life, and it's possible that there could be life in the liquid oceans of Europa at Jupiter or Enceladus at Saturn. We don't know. But the fact of the matter is until we actually go there, until we can actually perform an experiment or drill through the ice and stick a camera down there to see if anything swims by, we don't yet know. So that's really my best answer for you. Have no idea, but we'd like to think it's possible. We just don't know. All right, what else can I answer here? Let's see. Did I miss any other questions? I just want to make sure I'm taking care of you guys. Let's see. Will Mars ever be able to be habitable, considering what Elon Musk is considering to do, and especially since how climate change will affect the population of Earth on a worldwide scale? That's a really important question. Will Mars ever be habitable? So here's what you'd have to do. To really make Mars habitable, you'd have to, habitable as in Earth-like habitable. You can walk around without a spacesuit on. You can actually live a proper life. You would have to find some way effectively of stopping climate change here on Earth and making climate change happen on Mars. That's really what you'd like to be able to do. You'd like to be able to take all of these greenhouse gases that we're pumping into Earth's atmosphere and transport them over to Mars, or barring that, at least get Mars to start coughing up any trapped gases inside, any trapped greenhouse gases, namely carbon dioxide, right? That's going to be your heat trapping gases that will intensify Mars's greenhouse effect. That will raise the temperature of Mars, and that could make Mars habitable. So now the question is, well, how do you get those gases into Mars's atmosphere? What do you got to do? Well, what you have to do is either liberate them from underneath Mars's subsurface. We know there's a lot of water and carbon dioxide that's locked up in a permafrost underneath the surface. If there's some way to warm up the planet somehow to get those gases to start streaming out, they can potentially fill in Mars's atmosphere a little bit, trap some heat, then we'd have to add oxygen, right? We'd have to find some way of adding oxygen into the atmosphere as well. The good news is that we can make oxygen, right? There already is oxygen in Mars, and it's in the form of water. So there's frozen water. If we can separate the water from the oxygen, rather, from the hydrogen, that can pump a little bit of oxygen. Also, plant a lot of trees on Mars, right? They'll naturally outgas oxygen, provided there's carbon dioxide that they can feed off of. So terraforming Mars is nothing at all like a 10-year or 50-year endeavor as maybe depicted in the movies. Terraforming Mars is probably a multi-century project. It would be a very long-term project. So what Elon Musk wants to do is, and what others want to do for that matter, is just get the ball rolling. First thing you got to do before you make Mars habitable is that you have to get there. You just have to start, establishing colonies on Mars, and those will all involve, habitable bubbles that everyone's going to live inside that are going to be pressurized. You'll grow everything hydroponically, or you could even farm and till the soil of Mars, fertilize it, but it's going to be, grown in a protective enclosure. If you watch the show Mars on Nat Geo or National Geographic Channel, they've done a really good job doing like half science fiction, telling a plausible story that gets most of the science pretty accurate of a future colony, and I think in 2041 or something like that, living on Mars, setting up shop, and then switching back to present day and talking about the real challenges. As far as climate change here on Earth is concerned, one thing I'll just say about that really quick is that we got to stop it. We're in trouble. It used to be, we should be okay if we can stop by 1989, or if we can halt CO2 production by 2004. It's 2019. It's too late to halt it's too late to halt some of the major effects of climate change. We're already seeing Greenland melting. We're seeing the ocean levels rising. We're seeing the effects. Climate change is not something that will happen. It's happening now. The question is whether or not we can prevent the worst that's yet to come. That's going to be up to you, Zishan and Ava and everybody. You guys are going to have to be the ones who are going to make decisions, particularly when you're in a voting booth, of who you want representing you. Okay, let's see. What's more likely to happen? 1, to die via a lightning strike on Earth, or 2, to die on a meteor strike on Mars? That's a really good question. I don't know, Walt. I think honestly, well, you know what? Mars is smaller than Earth, and it doesn't have as much of an atmosphere to protect itself from meteorite strikes as Earth does. But I still think your chances are of getting zapped on Earth by lightning is a bit higher, particularly now that climate change is really, taking off and we're seeing more intense storms. A little gallows humor there. I'm for terraforming Venus. Step 1, adjust rotation to give equivalent Earth sidereal day by hitting it with asteroids. There you go. Yep. That would be great if we could get Venus spinning up a little bit quicker. Right now, its day is longer than its year. It takes 240 3 days to make one rotation, but takes 228 days to go around the sun. We got to speed that up somehow. And then figure out a way to dump out all that excess carbon dioxide, you know. Also, Mars is closer to asteroid belt, Vault asks. Yes, it is. It's closer to the asteroid belt. And that's, by the way, that's another way you can add more water, volatiles, carbon dioxide to Mars's atmosphere by throwing asteroids at it. Hey, if warming up the planet is too much of a pain, just go and get a bunch of asteroids that are already rich in carbon dioxide and volatiles and water and things like that, and hurl those at the planet. Yeah, absolutely. That is another way of terraforming Mars. Not well known, but even the IPCC predicts greening and economic growth for the first 50 years of climate change, then downhill. Obviously, they don't want to talk about positives, though. I'm not sure what that means, Little Cripple, about greening and economic growth for the first 50 years of climate change downhill. And I also, maybe you're talking about for the first 50 years following the Industrial Revolution. Yeah, absolutely. I mean, there was tremendous economic growth, by extracting oil and learning how to do that and burning it with coal. It built our present day society. Now what you end up with is, it's kind of a wash. You know what I mean? You could switch to a carbon-free economy. It'll put a lot of the oil folks out of business, but it also will add new jobs. And the economists have looked at this and they found it's really a wash. It's neither going to help nor is it going to hurt the economy. People just have to train, get different jobs. All right, let's see. So I think on that note, if there aren't any other questions, I've really enjoyed having you on today. Thank you so much for coming by. This was a lot of fun. If you would like to leave a comment or a like, someone was kind enough to put a link to my Patreon in there. Thank you very kindly. I really do appreciate it. And to my students, I'll see you guys tomorrow. Until then, thank you so much for dropping by and keep watching the skies. Bye, everybody. How do I stop this thing? How do I stop this crazy thing? Bye-bye.